Hello, everybody. I'm going to talk about something that it has been extremely, it has been talked during the entire Next. We have had several presentations talking about SLOs and error budgets. But I'm going to focus a little bit more into how everything applies once you get paged, once you're on call, and how you set up everything in a way that allows you to receive those pages that don't wake you up in the middle of the night. We're going to try to talk, sorry, my notes are I cannot see them. So we're going to try to understand the reality of complex systems, understand what matters to our business and to our users, understand tolerance, understand how to use symptoms as a way to page us, and then putting everything together. So raise your hand if you have ever been on call. Raise your hand if you have ever been on call in the middle of the night. Keep your hand up if you have been paged, and once you got to your computer, the problem was not there anymore. Okay, so you're in the right place, most of you. So first of all, monitoring is hard. As I was saying, there are plenty of monitoring systems that are alerting for things that once you get there, the thing is not there anymore. How many times has an ambulance been called to just show up, and then it was just somebody that had a little bit of a dismay, lose consciousness, but it's back to, or you call the fireman, the building is evacuated, and there is no fire. It's just somebody putting cooking or doing something similar. There are many times that you receive those pages, mostly because when you start a new service, when you start your company, you're working with small systems, you're paging for the causes, the things that are related to machine is out of memory, the CPU is very hot. Things that matter to your service once you start, but it starts not mattering so much when the service starts growing. The more your service grows, the more machines you have in your service. And there is a lack of correlation between how your service grows and how your operational, there is usually a correlation when your service size increases and your system has a certain capacity for the operational team. There is a bad operational situation if your operational load increases at the same level as your service size increases. The ideal situation is that your operational work grows sublinearly compared to your service size. And that is really difficult to do when you don't have the system-based alerting system that I'm going to describe continuously. Sorry, So as I was saying, alerting on CPU, I/O starvation, memory starvation, it's very normal to be done when you have small set of machines. But at data center scale, it doesn't make much sense. When you have thousands of machines that are running, imagine getting paged for any of those machines running out of memory. It doesn't even make sense at the level of the data center. People working in the data center should only get paged when a certain number of machines are running out of space, or when a certain number of machines are broken, not for every single one of those machines. When that happens, you're actually having data center operators running up and down in the data center, replacing a single disk on several machines. In fact, at Google, we have perfection, the idea of repairing a certain number of machines when they have to be repaired, and we actually trace the path that the operator has to do in order to go repairing those machines. So single cause alerting is definitely not a way to do it. In fact, if you do the math, I have here an assertion that 5,000 machines running for a single day is more than 10 years machine of a single machine running. So 10 years. In fact, it's something like 13.69 plus years. It's just a comparison. It's not a one-to-one comparison, but it's to give you an idea of how long a single machine should be running to compare to those 1,000 machines running in the data center. There are plenty of other things that you have to take into account, like the mean time before failure, and like the bathtub curve in like the beginning, you get a lot of failures in the machines because it's like new components and they haven't been tested. Then you have a flat line, and then you start like getting errors and breakages at the end of the life cycle. But essentially the idea is that running a set of a very complex system with a large set of machines increases the number of errors that you're going to get. So it doesn't make sense at all to page for a single one. In fact, one of the principles when we design the precursor of Kubernetes, Borg, it was that hardware failures is not a question of if they're going to fail, it's a question of when they're going to fail. So essentially what we did at Google was incorporating the idea of paging only when the user experience is affected. So we move away from paging from individual causes to paging only when there's a symptom that reflects user happiness. Only page when the user is being affected, when the user figures out that there is a problem with the system. So now that we know that we don't page for individual machines going down and we only page for when the users are being affected, let's talk about how we engineer that error that we are receiving and we are seeing in our systems, in our paging. Ben Traynor came up with the idea that 100% is the wrong reliability for almost everything. I would argue that it's impossible to achieve. In order to have 100% reliability, you would have to know exactly the state of every single of your components in your entire system at all times during the entire lifetime of those components. In fact, the user is not going to know that your system is not 100% reliable, because once you get into an elevator, who has a mobile phone? How many times you're in the middle of a phone call and then you get into an elevator and then you cannot continue that phone call? Exactly. It happens that error is introduced not only by the system but by your environment. So it doesn't make sense to try to embrace that, to try to fix those errors. It's better to embrace them because things will fail. Things will break, like during the natural life cycle of the things. You will have hundreds of users that will try to use your system when there is the final of the American football, when there is an earthquake in a different location. People will go to your service to try to figure out what's happening. People will go to pay when there is a dip on the Bitcoin or to get the Bitcoins out of your system. Also, users will try to use your service in a way that it was not designed for. Google Maps had a certain peak of use when people figured out that they could get the tiles of the maps and then start using them for other purposes, just to put the location of your business. So we had a huge spike on the traffic, and we had to include some authentication to avoid that. But we had an outage due to that problem. Also, people will use your service in ways that you were not designed, and people will actually abuse the service by hacking your system, by getting inside and bringing down your database when you're less expected. Very common to have SQL injections that suddenly delete your entire user database table, and you cannot access your service anymore. In fact, even Google fails every now and then. You barely notice it because it fails very little, but it fails. So the thing that we introduce to account for that failure is service levels. It's not avoiding error, it's introducing error in your system in a way that you can account for it, so that even if error exists, your users can mostly operate and use your service in a way that it was designed for. Those concepts are probably the most important thing that I'm introducing today, but it's they're pretty much in every single literature that we have written, in the 2 SRE books. It's a service level indicator. It's a metric. This is the first concept that we're introducing. It's basically a definition of an attribute of your system. An attribute of your system being a way that your user is using your system. It's exactly what it says. It's like it's an indicator of how the service is performing at a certain point in time. An example of that would be like the proportion of HTTP GET requests that you can get on your homepage. There are 200, 300, 400, excluding a certain measure, but it's measured at the load balancer. That is just the indication of how the service is performing. A server level objective is a service level indicator with a specific goal. So a goal could be that 99.9% of those requests are successful in a certain period of time, like 28 days. There is another concept, which is service level agreement, which is basically a contract that you have between you and the users of your service that are paying for it, in a way that, like, if you miss the SLO, if you run out of error budget, then your users get a certain type of compensation. So now that we have a definition of an indicator and we have a goal for that indicator, like a certain level, how can you find that level? So a way to find that first goal, if you don't have any data of your service, like you're new introducing your SLOs, the way that you can do is look at your past. The expected performance that you have in the present is the performance that your user have experienced in the recent past. So that's something that you can use to define that first level of performance that your service is providing. It's something that you should not maintain ad infinitum. It's something that you should change because expectations change. Past performance is not an indicator of future results, so you should go back and see how the system is performing at a certain time in the present, only to change when the environment changes. Imagine trying to get your phone out of the pocket, and it's an iPhone 2, and then connect it into a GPRS network right now, and trying to download your favorite website. It will probably be a nightmare, and then you will hate that experience. So things change, even though you don't feel that the website is changing. They're loading it with JavaScript, they're loading it with like more requests in the background. So things change in time, and therefore you should be analyzing how those things are changing and get to the future. So now that we have a certain level in which we can assume that the service is going to fail, we have, for example, 99%, 2 nines for your service. You have a certain leeway in which your service can fail. So the point is not to avoid that failure, is to embrace it. And once you embrace it, you can use it for other things. Like you can test your environment, you can test your users, you can do A/B experiments, you can increase the level at which you, the speed at which you release new features. You can put that feature that you were not expecting to put because it's a little bit too risky, but then you can put it there and see how your users are affected. So now we have what we are trying to measure and how we are trying to measure. So let's talk about how we alert on those measurements that we have. First of all, we said that a symptom is anything that you can measure with a SLO. So a way to express that SLO would be to measure like the uptime of your service. That's the availability. So you measure how long it stays up compared to how long it stays up and stays down. That is fantastic for a single machine. But then we go back into the complexity of the systems. Like once you have your load balancers in the front, you have all the 1,000 machines responding in the back, it's almost impossible to identify that binary in which you're like identifying the uptime. So what we do instead is we define the availability in a complex system as the amount of errors that you receive when you're receiving traffic versus all the total requests that are valid when you're receiving those requests. So then you have your system, you have your SLOs, you put a prober, your prober is testing your machine every 5 minutes or every 1 minute, and then your system is telling you that your system is up, you have your availability numbers that are like 100%. We're done, right? No, we're not right. Imagine that you have a cron job that is running every minute, and it's like loading your service 10 seconds of every minute at the beginning of the minute. And then you put your prover that is only testing your service every other minute, and they interleave with each other in a way that only you're getting the good pings, but not the bad pings. That is possible to happen. So in order to increase the resolution that you obtain from your prover, the thing that we recommend is increasing the resolution of those probes without increasing too much the traffic that you're creating. Another way that we can use is measure the availability at the application level. You instrument your application to save logs on the requests that you're receiving and the responses that you're providing, and you can increase the coverage of the measurement of availability. The problem that you're introducing over here is that you only account for the good requests that you receive. All the requests that died at the load balancer level or died because the network was down, you won't be able to see them. There's an expression that I put over here. It's essentially Prometheus expression, in which like you're just like you put this in your Prometheus code, and you can see like the availability in the right numbers, like essentially counting the requests that you received, discarding the requests that are 400s, and then doing the calculation. Another possibility on how to measure the availability is by doing it at the load balancer level. You put your measurement in the load balancer, which is like account the ratio that you receive, count the responses that you respond versus all the responses that come back from your backend web servers and are not 200, and voila, you have a measurement. Right? We made it. We have all the symptoms that are calculated. We are creating alerts that are paging every time that we are seeing an error on the availability of our system, and then happy users. Not so far. Once you start paging for every single error that your service is seeing, you're basically counting every drop as if it's worth the same. And that's not reality. Like a machine that is dying in the background, your load balancer is not fast enough to move to a healthy machine. Your high availability service is not accounting for those little glitches that happen over there. You don't want to page for every single failure that occurs in your system. What you want to page is for the SLO burn. It's the ratio at which the error is being produced. So big floods of errors are accounted for. Small errors occurring in isolation are not accounted for. How do we do that? We introduce a little bit of math. The thing that you want to calculate is the burn rate at which you have, you define a threshold in which your error rate is basically burning your entire error budget at the end of the window. In this case, if we have an average QPS of 1,000, what we can do is like, if we have an SLO of 99 over a period of a week, we calculate that we have a number of 604 million total queries, and therefore we have a number of permissible errors of 6 million plus. The idea of calculating the fast burn error rate is by calculating that threshold on how many QPSs are per second. In this case, the threshold would be about 70 errors per second that your system is producing. So what you do next is define over that threshold, you define two regions. The one region in which like your fast burning of error budget is going to consume the entire error budget at the end of your window, and then the area in which you have a slow burn, but at the end of the error window, at the end of the time window, you're going to just burn a smaller amount of that error budget. However, consuming that error budget in a small amount will also produce introduce some problems, which is that you will not have that error budget to experiment and to do other things. So what you want to do is, in the second part, is you want to introduce a level of in notification, like send a ticket to your operational team so that on Monday when they get to work, they can take a look at it, but they don't have to respond immediately. On the other hand, when you receive a fast burn alert, that means that you are affecting your users in a way that your error budget is going to be consumed by the end of that window, and therefore it's something that the system is being affected by. It's something that is like if it goes immediately to failure, that line, that blue line, by the way, I didn't ask, but anybody is like colorblind? Anyway, the line on the top that says fast burn, that is a line, in this case, it's a line that is like very similar to the threshold of your error budget consumption. But if you have a full outage, that line probably is like almost vertical, unless you're in the middle of the night, and then you're just receiving very small QPS. But still, it's something that you would like to respond, because the moment that you increase the QPS, that line will be almost vertical and will be consuming your error budget almost immediately. There's an expression that I put over here. It's basically Prometheus, so it calculates the errors that are produced in a period of an hour. You would get paged when the amount of increased errors in that period of an hour is bigger than that threshold line of the error budget. And here are the calculations that we put before. It's like the number of QPS that we're receiving in a period of time compared to your target availability over a period of 24 hours. So putting it all together, once you define how you want to measure, what you want to measure in your service through your SLIs and your SLOs, when you have your availability target that you have defined either through past experience or through observability of your service, what you want to do is not forget observability. Like that old system that you're using right now, which, by the way, I tend to call it the Nagios problem. It's like when Nagios came out, it was so easy to just install it in your machine, put an SNMP server, and then immediately you would get like your CPU metrics, your memory metrics, your swap consumption. Like, do not forget about that. It's something that it might be important to do correlation and to debugging your problems, but essentially, like, use the 4 pillars of observability that we have described before. They are like logs, metrics, traces, exceptions, core files. Like, collect that information. It will help you to maintain that information to do correlation and causation and root cause analysis. But move to the alert to the system-based alert system. By doing that, you transition slowly. Like, talk to the team that is writing the software and see if you are collecting logs. Talk to the people that are in charge of the load balancers. If you're using Google Cloud, many of the load balancers automatically ingest that information into Stackdriver. So figure out what is the information that you want to page on. What are the like metrics that are defining how your service is operating? Introduce a couple of SLIs on them. Introduce a couple of SLOs that define your objectives, and then start measuring that availability. The transition assumes that your teams are having all kinds of like it works in a coherent manner. Like, introducing SLOs and targeting availability requires the development team in order to do the thing that we were doing, that we were talking about. Like, once you burn your error budget and you don't have reliability leeway left, you have to get your teams, to development teams, to slow down in putting new features, slow down in like pushing for those releases that may increase your risk. Like at Google, we have identified that introducing new changes, and even if it's configuration changes, releasing new binaries, increase the error that is being added to your system. So add a system-based alert, lower the severity of the system-based alert in the beginning, and then identify if you have an outage that is being paging through your cost-based alert. If the system-based alert is also paging, identify the moments that your alerts are firing in the cost-based alert, but are not firing in your system-based alert through your SLOs. Maybe your users are happy and you're just paging your operators without any reason. And slowly transition to increase the severity of the SLO-based alerting system and decrease the severity of the cost-based alert once you feel more comfortable with it. The next thing that you should do is those goals that we have defined before, analyze them. The analysis is done through critical user journeys. So get to your service, talk to your developers, identify what are the things that are extremely important to your service, and based on those, identify some of the SLIs that increasingly will, that over time will increase in complexity. In the beginning, you should aim for like the basics, like the simple things that provide you the biggest amount of information. But later on, you will like introduce more complex SLIs, like a system like in which you have to do a login. It may have certain interactions with like taking authorization tokens, bringing them back, calling some other databases, some external service for payments. So increase the complexity of your service once you get comfortable with that. And the next thing that you do is you rinse and repeat. SLOs should never be set on stone. They change with your users, they change with the development of your features and your service, with the growth of your service, with the importance of it. Like you may be the leader in the market and a lot of people are relying on you. So you need to like move and create that culture of like revisiting and reviewing what you have defined so that you can move as your service moves. And on that, there's much more information about this topic in the 2 books that we have published. There is a URL over there where you can actually get the copies of the book in PDF. And we have also a Coursera course that goes through the entire workflow on how to develop those SLIs, those SLOs in much more detail. You have the URL so that you can access it over there. And with that, you made it to the end.